Can I go? I can go. Right. So just in broad strokes, what's going on with this lecture series? There is I want to present some modern operatic approach to a classical topic of deformation theory, and without even saying exactly what I mean by deformations for the moment, maybe you can keep an intuitive idea in mind. The idea of deformation theory is that you want some, we're interested in some X, some algebraic or geometric object, and we're interested in some sort of infinitesimal families xt that correspond to our deformations of X, and so such that whenever you evaluate at 0, you recover your X back again. So if you, for some visual picture in mind, you can think of you have maybe a big variety and some subvariety in it that will be our X, and your deformations can be maybe a family of subvarieties xt that when you get back to 0, then you find your X back again. So this would be maybe
geometrical example. And
Oh, fuck. Shit. Sorry. Seriously?
okay. So
this is
example 1. Example 2 would be something like you start with some associative algebra, and you want to deform it in the world of associative algebras. So this would correspond to having some deformation parameter. So that maybe I will call it h bar, and some product deforming the original product on A. So also associative, and the deformation property here would mean that when you compute this new product on two elements AB, you would recover the original product AB, but then some deformation of it, like H times, I don't know, something, let me call it B1 of AB, then plus H square of something else. So when you evaluate at H bar equals 0, you recover the original object. So there is, so if I change cameras, is it, okay, that's fine. So there is this deformation theory philosophy dating back to, I don't know, I can name drop a lot, Deligne, Greenfeld, Kontsevich, Manetti, Manin, Hinich, Schlesinger, lots of people. So I'll make sure that these names appear in the lecture notes, but the slogan is in characteristic 0, deformation problems are encoded by differential graded Lie algebras, and in more recently, this has been formalized to a proper to a proper theorem by Lurie and Freedom. But somehow for many applications, you don't actually need a formalization of this problem. So it's of this philosophy. It's a very powerful slogan in itself. And what operatic calculus buys us is a very powerful way of finding such Lie algebras, of reinterpreting deformation problems, and gives you powerful tools to address them. So that's more or less what I want to address in these lectures. So a bit more concretely, the plan for this lecture series is in lecture 1, so today, I will be doing the algebraic operad part, so the algebraic operadist toolkit. On lecture 2, I intend, so today I'm going to develop a bit the theory that we need, so it's a bit more technical in some sense. Lecture 2 will concern some more hands-on operatic, some hands-on deformation theory, I guess. Where we'll try to reap the rewards from what developed earlier and apply it to some concrete examples that should show that it was worth spending an entire lecture on the backgrounds, and some applications also to rational homotopy theory. And on lecture 3, that I call it formal moduli lecture, moduli problems lecture. I will talk a bit about the formalization of the deformation theory slogan. I will show how this is related to causal duality and talk a bit about what happens in positive characteristic. So that's in broad terms what I intend to do in this lecture series. So I think now we can start to lecture 1. So mini course rules apply. You're supposed to interrupt as much as you want. And if I have to stop on half of lecture 3 and I cannot do everything, it's not a problem. It's more important that we learn something out of this. So far, it's clear, yes. So I also decided on some working assumptions, which is that this is a workshop called Higher Structures in Operatic Calculus. So assume that people are familiar with operads, or at least interested in operads, but maybe not as much with algebraic operads. So algebraic operads are their own worlds somehow. And I intend to start with some recollections on algebraic operads. So assumptions. I guess conventions. We always, unless otherwise specified, we work always with a field of characteristic 0. And our underlying, everything will happen over chain complexes or co-chain complexes over K. And I will frequently forget that this is the case. So whenever I say words like vector space, it's likely that I mean actually a complex. But that's otherwise all that is assumed. So let me remind you that there is this notion of symmetric sequences, which is just a collection of vector spaces, chain complexes, indexed by some natural number, with some bright action from the symmetric group sigma n on each mn. And these sigma sequences form a monoidal category with this famous circle product, which is defined arity-wise. So I guess this is non-terminology, but this n I denote by, I'll call it arity. Yeah, sorry. Also, my handwriting is not the best, so this is also a reason to interrupt me if at some point it is not clear. There is this product defined on symmetric sequences, which takes mn and will take the sum over all possible k's of sk, and then you fill 1n for each of k. So I1, and it's still visible here or not? Okay, perfect. This, and we take some coinvariance, but first we need to induce this from sigma I1 ik to sigma n. This, I will avoid writing formulas of this sort. I will just prefer to always write this as trees. So we should picture this as a tree, that's a two-level tree such that the bottom level, which consists only on one vertex, is labeled by some element in M, and the upper level is labeled by elements in N. Okay. So bigger means this tree is too small, or does it mean that, yeah, letters are tiny? This is probably already the case for people in the lecture room. Okay. So with this monoidal product, also just there is an identity which is just field K in arity 1, and given this, I think it's only fitting that the first definition of this talk is that the one of an operad. So an operad is a monoid in this monoidal category. So sigma sequences with the circle product and this I. So an operads will always be denoted by P. So it's also convenient to fix a bit some terminology. And so what we're saying is an operad is a way of assigning two-level trees to one-level trees. But what you might also be familiar with is that this is equivalent to another definition of an operad, which is the so-called partial definition. So it's a collection of maps. Yes, bigger. Okay. Okay. Collection of maps. Circ I from PM tensor Pn to Pm plus n minus 1 for I equals 1 to the entry point to M. So what I'm saying in short is that we can essentially either say what is the single composition we can either say what is the single composition here and assign to this just one single element of P, or we can say we can decide what's total composition with multiple elements of P. So I'm being a bit insistent with this because it's something that people sometimes don't pay a lot of attention to, and they know that there's some sort of partial definition of an operad and a total definition of an operad, but they're somehow really allow you to do very different things in spirit. And already the first example of this is when you consider algebras over operads. So an algebra over an operad is, or I guess first, a module over P is, we denote it like this, but it's just a module in the sense of a monoid. So it's maps P circ M to M. And so for M symmetric sequence, if but more commonly we're interested in the case where M is really just a chain complex, and if M is essentially concentrated in arity 0, so it's given state of complex. We say that we'll just use a different word, and we say that M is an operator.
Pásame el host si quieres tú, no sé. A ver, lo tenemos aquí.
So what I want to point out is that while this is just an immediate definition with what we have, if we wanted to use the partial definition of an operad, it's actually very complicated to define what an algebra is, right? If you try to replicate the definition of what an algebra over an operad is with this partial definition, you would more likely end up with something that would look like that would associate to an element here something in A. And this is not at all what we want to do for the moment being. So by the way, this is, I think, what's normally called a partial module or an infinitesimal module over P. Um, yes, I think it satisfies a lot of things that I was, yeah, sorry. This map is, maybe I should have written this. So what this map is supposed to satisfy, it's a monoid, which means that you're making elements you're acting with P on M and getting back something on M. But so this has to be compatible with the operatic, the operad structure, which is itself monoid for this circle product. So what you would like to do is, if you do something like this, you would actually, well, by composing, by using this module structure, you would end up here. But then you can compose again, and you will end up in M. Now, what you could do differently is you could start by doing this, and then you would also end up in P circle M, and then you can compose again. So the condition is that you require this to commute. In drawings, what this actually means is that, so what is this? In terms of trees, you have sort of through-level trees. So you have a first element of P, down here, and then in each of these top vertices, you can make you put more elements of P. So maybe here, just to simplify, let's say that here you put elements of sorry, this is being too small, right? So you have when you have the circle product, you should be representing it in terms of level trees, and then what just changes is on each level you label every vertex by elements that are there. And what you want to do is you want to associate such an object to something that is pictorially just a one single level tree. Maybe here. So essentially the definition is you can actually just draw these trees, and saying that it's associative means that you don't need to worry if you do first this and then that association, or if you do the bottom one and the top one first. So this is the picture that one should have in mind. Is this fine? So exactly this description in terms of trees means that the fact that an opera is just saying you can draw trees and insert them, and you don't need to put any sort of parentheses on the trees. This means that that given such a symmetric sequence M, one can define the free opera on M as so what I will denote by a T a bit italicized on M. Is there a problem?
You don't talk now. No. Yes, not using? Yes, so? Okay. Doesn't come. It works now. No. No. Right.
Is there a machine running in the background? And is there any other thing causing a beep periodically?
Hello, it's connected. Yeah.
I heard your voice,
But with the, I don't understand anything. C'est bon. Oui, parfait. Voilà, allez, c'est bon. Ok, il y a l'écho. Il y a l'écho. Oui. Voilà. C'est un point. C'est toi qui. Mais c'est pas grave. Parfait, parfait.
Je pense que ça marche. I think it's no longer turned on. Yes, it
If
is.
someone want to talk. Okay. Non, non, mais là c'est vrai qu'il y a de l'écho. Il faut. We can change it. We should. Yeah. This is off now. We have here.
Okay.
On va parler.
Okay, so given this, I should be finishing by at around what time? Okay, 3 hours. Right. Okay, so all of this is essentially just to say that at the end with operods, you're actually doing combinatorics in some sense, because you can express everything in terms of trees, and this is reflected by the fact that the free operod on a symmetric sequence, so the adjoint of the forgetful functor, is precisely given by, without being very precise, by arbitrarily, so just by trees with whose vertices are indexed by your original sequence, where, well, here, maybe I should have just mentioned this before. Here, this has 3 exits, so this should be indexed by M3, by M2, M2, M3. So, and this is very convenient because actually we use operods to study algebras, and it turns out that algebraic structures that we define are defined using properties. So there are just the classical examples. For instance, the associative operod, which like this can be very simply expressed as, so what's an associative algebra is something that has a single generator, which is a product, something with a product that should satisfy something, and what it should satisfy is an associativity relation that under this expression just is just written in the following form. So one should be just slightly careful with the symmetry. So this has to be this has a symmetric group action. So I actually should want to distinguish between the 2 different products that one can form with 2 elements. So that I will just denote them by the product where you multiply things in the right order and where you multiply things in the opposite order. And then, yes.
But if you do the distinction, you also need to symmetrize the derivative.
Yes, I will not do this. And just to fix some notation. Similarly, you have some Lie, some commutative operods, and I will avoid as much as possible to consider operods that have units, even though, just as a quick example, things become a bit more complicated when you consider the operod of unital commutative algebras, which then would be something that has both product and some unit, which is represented by an arity 0 element that I denote by putting this sort of cork here, and it satisfies some properties like associativity, but some more awkward properties of the form, so not properties, I guess, relations
of the form this. So if you product with the unit, you actually get something which is the identity. So this will actually be playing a role in the future, but not today. It's the wrong camera on.
I mean, it's good. Why is it?
Okay. But so the fact that we're doing vector spaces actually isn't playing any role until now. But one part where it actually does play a role is that note that that our underlying category, chain complexes over K, is not only monoidal, but it's closed monoidal, meaning monoidal. So it satisfies some natural adjunction between the hom and the tensor product. Okay. So this actually implies that there is something that does not exist in other categories. So there is a notion of an endomorphism operad. Oh, yeah. I was going to write endomorphisms of A. So I will keep M for a module and A for just a chain complex. So endomorphism of A is an opera that in RATN is just linear maps from A tensor N to A. So the fact that we have this changes a bit the idea on how we should think about our objects. So an algebra now is in some sense an algebra over an opera is not just a module over the opera, but an actual representation of the opera. So what I mean is that A is an algebra over P ends up being equivalently given by the data of a map from P into the endomorphisms of A. So this is something that ends up being crucial because it allows us to work with endomorphisms of A, plays an important role when later we'll talk about things like the homotopy transfer theorem. Okay. So it should also it also allows us to do something funny, which is operads are monoids. You expect monoids to have modules, not so much comodules, but there is also the co-endomorphisms operad, which is now coend of A, where you reverse what I just wrote there. So you map A into A tensor N. So I didn't mention that the operatic composition here is just composition of functions. So, and it should really be stressed out that that it's an endomorphism operad and not a co-operad. But the notion of cooperate is also playing a very important role in the story that I want to tell you, which is, so it's not very unexpected that what I'll write now, but if an operad is a way to make compositions like those trees with many vertices into one vertex, a cooperad does the opposite, but not exactly. Is now a comonoid in a different category. So you have a slightly different composition product, and this is essentially you want to allow you want now to allow an infinite number of things. So you don't want to take the composition with a direct sum. So here you just have exactly the same as circ. In other words, if you have something like this, you can actually co-compose it. So cooperad C. Cooperad is a rule to make C. Yes.
I'm not sure that this round product forms the monoidal category. It's not associative.
Yeah, I agree.
You can repeat it on the microphone for people.
Right. So there's actually some subtleties that will play an important role. This is not really a monoidal category because products and direct sums do not commute at infinity very well. But we can still take this as a definition, and I'm trying to give here the good intuitions and what will be problematic, and this is not a problematic point because in any case we will essentially be restricting ourselves to cooperads that have nothing in arity 0 and 1, and when you have nothing in arity 0 and 1, for the moment this will be fine. But I still want to talk about this product because we not because of the operads, but because of coalgebras over operads. So without writing too much, you say that C is conilpotent if delta can co-compose non-trivially only a finite number of times. So at some point, if you continue co-composing, you would get 0, except that you do not actually get 0 because of the unit, but that's the only non-zero piece. Non-trivially only only a finite number of times. And then a coalgebra over C is A equipped is a complex A with maps A into C circ hat of A. So what we should see here is that A can really co-compose into a product. So it can actually be very large. You can also say this is actually just equivalent to something that I wrote before. This is equivalent to so even without finite dimensionality assumptions, the dual of a cooperad is an operad. And this is equivalent to just a morphism into these coendomorphisms operad of A. So it's quite convenient that somehow you can restrict back to the language of operads to talk about coalgebras. It's the linear dual. RETY is linear dual.
And go on the co-operad?
Operad, not a cooperad. So no, exactly. So the linear dual of an operad of a cooperad is an operad always, and coendomorphism is always an operad. It is maybe not intuitive that it's not a cooperad, but okay, that's life. So the last.
What is equivalent?
It's equivalent to a map.
No, just in words. What's the statement?
Yeah, the statement is coalgebra over C is something of this form compatible with a comonoid product. Let's say that C will always be conilpotent, but for this specifically, you do not need to require this. And this is equivalent to a map of operads. So what I just wanted to say is that you kind of dualize this into exactly a morphism of this form.
I'm sorry to disturb you, but if this were true, then you would have the co-free coalgebra by your construction C circle at A, which is wrong. It's
Yes.
a pullback of that. So
yes.
the definition with the circle at is all wrong. No offense.
Yep.
This is not a monoidal product. But this is very good.
Yeah, but I mean that's the whole problem with this story, right? There's no really satisfying definition for.
No, there is.
Cannot be equivalent.
Right?
You mean that? Okay, sorry, you're saying that I said that this is true even if it's not conilpotent?
Anyway, this is wrong. The last point is a good definition. Take it. This is not well defined. The circle hat, as Victor was saying, is not a monoidal product anyway. So
right.
It is more subtle. If you want to work with product instead of direct sum, it's more subtle than what you wrote on the board. So heuristically speaking, you can keep that in your mind for a second if you want, but it's not a proper definition.
Right. Sorry. So it's always the direct sum product problem, right?
No, the direct sum is okay.
Yeah.
But if you work with the product, then this is not anymore a monoidal.
Yeah, because of the non-compatibility. Yeah.
Exactly. What
right.
condition do you impose on your map from A to C? What condition of coercivity?
If it factors to that famous pullback, then this is okay. Right? Well, let's not go into this detail right
now.
now.
Exactly. So my goal was to try to give intuition, and somehow this is the kind of details that I want to hide under the rug. Yeah. No, it's very subtle. It's a very subtle point, and honestly, I don't think it will add much to the understanding of what we're trying to do here. So. But I was talking about conilpotence. So conilpotence is also defined for algebra. So A from before is conilpotent if for all A in A and the co-composition of A. Maybe I should. Maybe this should be the map. Delta is 0 for sufficiently big delta. So for sufficiently arity big delta. And what I just want to say is that this is somehow very restrictive, or kind of restrictive maybe, compared to conilpotency for operads. Because essentially, you take any example that you can take very simple examples. So finite dimensional, for instance, does not imply any sort of conilpotency for algebra. So if you take the commutative coalgebra K, the base field, so equipped with just the most trivial product, sending 1 to, well, it's the identity, 1 to 1. This is not conilpotent because you can just iterate the co-composition, you get something non-zero. Now you might complain, oh yeah, this is a problem of units or something, and you can just get rid of the units. I will not only say that your complaint is not so much valid because we're working with commutative algebras and not with unital commutative algebras. But if this is really not satisfactory to you, just take the simplest Lie algebra that you can think of that is non-trivial. So maybe the Lie coalgebra obtained by dualizing SL2. So this is three-dimensional and is also is not conilpotent. So it is maybe a bit surprising that this notion of conilpotency is still very useful. But one should keep in mind that it's somehow restrictive if you, so yeah, if you just dualize a random algebra, you will likely not obtain something conilpotent. Right. So getting more algebraic, there's just some notions that I want to talk about, namely convolution and deformations. And let's all work from now on. The convention is operads or cooperads today have nothing besides the unit in arity smaller than 1. So convolution is something that you can define for given a cooperad and an operad P and a cooperad C. You define their the convolution operad conv C to P, where conv in arity n is just the linear Hom from Cn to Pn. and the operad structure. So it's I called it an operad, right? So the operad structure is given by the following. So given f g1 gn in conv of C to P, how do you define f composed with the g's? It is something that, well, it should start from C and end in P. So what you can do by starting with C, you can co-compose in C and get to something in C circ C, and then you can apply f to the first term, and then g to the other terms, and end up in P circ P, and then you take advantage of your composition in P to end up back in P. So this will end up being actually a rich source of examples for the operads we want to use in our deformation problems, because of another notion that is the one of totalization, which is given P, an operad, you define the totalization of P to be the product in all arities of, so it's a total space of P in the sense that you just take all arities together and at the end take invariance. So this is a priori just the product as chain complexes. It even has some additional grading, if you wish, given by this by the product. But this turns out to be a Lie algebra. Lie algebra, is this big enough or is it too small?
It's very fine.
Yes. Via so you want to bracket if you want to bracket elements P and Q, so I should be defining this on the product. So it's some anti-symmetrization of something, Q star P, for maybe, let's just assume that P and Q are in some fixed arity. And this star, I will just, sorry? Where P star Q is given by a picture that is just the sum of all possible insertions of this form, PQ, without writing some indication. So essentially, you could insert them in all possible ways, but it's not just the sum over all partial compositions, because there are just some details concerning symmetries. But this is the picture one should have in mind. But the important part is that so this product. So remark, and it's kind of a very important remark. This is not associative. So normally, when you get Lie algebras out of anti-symmetrization of something, this is this something ends up being an associative product. But that is not the case, but it still turns out that this product is giving you a Lie algebra when you symmetrize. And well, what this is, that satisfies a weaker property. So let me just write. So the associator of 3 elements x, y, and z is not 0. Well, I'll just write out in a second what the associator is. X is not 0 but left symmetric. So by associator, I mean x star y star z in the two possible ways of associating the elements. So minus x star y star z. So this is called being pre-Lie. Is pre-Lie. So it's a pre-Lie algebra. So not good enough to be associative, but it's still something that satisfies antisymmetry. And I would just like to, because it's kind of good combinatorial practice to see exactly what the problem is. So the problem is in pictures. What is this? What is this associator? This associator is, well, you have P, Q, and W, and you're plugging them all. You're plugging them all together in some order. So what you can do is you can maybe plug Q in P and then W in Q if you start with this. But you could also alternatively plug in W in P instead. So if W gets into Q, then everything is associative, because the Operadic axioms tell you that it's fine to first do this and then this, or vice versa. But now if you do it in the other order, you will not have this in the other composition, because you first have to plug W into Q. So this is not in W star Q star P. So it's a problem of a failure of associativity. But what you see is, well, if still you do it in the two possible ways, if you commute the associator, what you end up getting is W and Q standing side by side, so it doesn't matter in which order you plugged in W or Q. No, seriously, Bruno, until when should I talk?
Maybe 11 now.
11?
If we switch everything by 30 minutes, it's okay.
Okay.
You and that's another reference. It's open for one.
Right. Okay, so I'm spending some seconds talking about pre-Lie because this is actually playing a very important role tomorrow. And the Lie algebras that we're going to construct will end up being some sort of iteration of procedure like this, by starting with a co-operad, and then operad, you do convolution, and then you end up totalizing So if there are some questions about this here, it's a good moment now.
For a moment, I see the link between convolution and totalization. For a moment.
No. They're completely independent. I'm just saying that we'll end up totalizing things arising from convolution. Yes. So a priori, the two things on the blackboard, they do not speak to one another. It's just that they will be used together. So now we get to bar cobar, and what we will consider is there is an adjunction called bar and cobar from conilpotent cooperats and operats. And here there is the cobar functor. Here there is the bar functor, and they work like this. And the way these are defined is take here a cooperat conilpotent C, or and then you define cobar of C to be so the free operat, as I was using before, the notation generated by C as a symmetric sequence. So you forget that C was a cooperat. Maybe remove a unit. So this is C modulo the unit, and you shift. Let me just check under. So I should just be consistent with the shifting. So I'll shift it like this, and my differential. So I'll shift it up, and my differentials will be will have degree +1. So it's.
You're working cohomologically?
I work homologically.
Cohomological.
So there is a cobar differential, and so as an operat without differential, just the free operat generated by this. And where d cobar, so the differential is enough to be defined on generators. And so on generators, what you can do is actually make use of the operatic, the cooperat structure on C. So what it will do is you see C as you do a single partial co-composition on C. So it's one of the important points where there is kind of where it's important to distinguish between a partial composition and a total composition. So what you do is this is the infinitesimal co-composition given by C, and you extend it to the whole of C by derivations. So you'll end up verifying that d squares to 0 from the, say, co-associativity axioms. So of C. Because what you do is you co-compose once, you co-compose twice, and it kind of doesn't matter where you co-compose, but since there is this degree shift, there will be some signs appearing, and it turns out that the two things that you got have opposite signs. So this will end up squaring to 0. And in the other direction, it's very similar. You if you take P and operad, the bar construction on P is the free co-operad. So it's given also by trees on P, you remove the differential and you just get, you do the same thing. You have a differential that will extend now the composition. So now it's a co-free co-operad, co-nilpotent, and the differential is uniquely defined by projecting on generators. So this is dB extending just an infinitesimal co-composition. Same thing, it squares to 0. Yeah, I guess let me just write down the degrees here are +1. I said it orally, but and dB squares to 0. Now, this adjunction turns out to be very, very important, and it satisfies very nice properties. And I haven't justified yet why this is an adjunction. But what you can see is so proposition. So maps of so what we want to show? We want to show that maps of operads from cobar of C to P are equal. So let me write something in the middle. Are equal to maps of cooperads from C to bar of P. So whenever I write cooperads, this is always living in the world of conilpotent. Anyway, it doesn't matter because I said from the beginning that. Yes, thank you. In the beginning, I said that everything will have nothing in arity 0 or 1, so it's fine to take this assumption. But so the whole point of these constructions is that they are up to the differential, they're free objects. So if we're just willing to forget the differentials for a second, so this actually lives in maps of non-DG operads from cobar of C to P. And but as non-differential graded objects, this is just free. So you know that this a map of by definition of free is just given by mapping generators. So this is the same as a hom of vector spaces of complexes from C bar into P. And
Ricardo, sorry,
yes.
what do you mean non-DG operads? They're not, I mean, cobar is, you're shifted, so.
Yeah. I
at least graded, right? So.
yes. Yeah. No. You're right. It's just up to differential. What is a better way of saying this? Very good. Yeah, but right. So I actually mean without just the extra differential, because C itself can have some internal degree. But okay, as graded operands, it's this, and actually let's hide it a bit under the rug, but you just kind of get rid of the identities everywhere. So up to this tiny detail, the two objects coincide, because here you can also go into graded cooperats and these objects downstairs, they correspond. So the question is, what exactly is up here that corresponds to both of them? And what is up here is, well, now remember what I mentioned before. Actually, this home is what is this home? Is actually a home for all arities, Cn, n, n, and these maps actually have to be compatible with the symmetric group action. So it's actually just a map of k sigma n representations, because yes. But so you realize that what I wrote here is actually exactly the totalization. It's the totalization of something, because sigma maps that are compatible with the sigma n action are just a sigma n invariance of this thing. And the object the opera that is plugged in there is exactly the convolution opera. So this is a Lie algebra. And inside of this Lie algebra, there lives the object that corresponds to that makes this this whole diagram commute, which are the twisting morphisms from C to P. So this is both a proposition and a definition. Twisting morphisms from C to P are the set of maps alpha from C to P of degree 1 of degree 1, exactly, such that they satisfy some equation, and the equation that they satisfy is the so-called Moore-Cartan equation. So if there is one important equation in the entire lecture series, is this one. So this even warrants a proof, which is really not complicated. You just need to interpret what's going on in there. So suppose you have. So what does it mean? So what we need to verify? Sorry, for this equation to for such a map to induce a map of operats on both sides. So it just needs to have the right degree and commute with the differential. Having the right degree is written here, because remember, there was actually a degree shift in both the bar and the co-bar differential. So it's not degree 0, it's degree 1 written like this. And being compatible with the differential is essentially saying that alpha of the co-bar plus the internal differential on C, which perhaps exists, is the same as first applying alpha and then the differential on P. And then you can write this out and see that, well, the co-bar, what does it do? It splits out our operad into two. So actually now you have two vertices. So when you're applying alpha to the image of the co-bar, what you're actually doing is doing some alpha tensor alpha on this composition. And well, then alpha on DC is just alpha DC. And then you can move this to the other side and you get dp of alpha. But well, then, sorry, equals 0. But then you observe that this is exactly just a definition of the Prilly product that I defined before. So this is actually just alpha star alpha. And this commutator is just a differential on a home between two chain complexes. So this is d of alpha equals 0. So just one tiny remark is that our element has degree 1. So in this case, so alpha bracketed with alpha because of the degree differences is not 0, but it's 2 times something somehow. So this is just the bracket of alpha with itself, and that is the proof that an element satisfies the Moore-Cartan satisfies the Moore-Cartan equation if and only if it induces a morphism either from the co-bar construction to an operad or from a co-operad to the bar construction, which allows me now to maybe go back a bit into this whole philosophy of deformation theory that I was mentioning in the beginning. So we do a kind of a Moore-Cartan detour to recall the philosophy before. In a bit more detail. So I said that the philosophy from deformation theory is that Lie algebras. So a Lie algebra G is encoding a deformation problem. And under this vague correspondence, the solutions to such a deformation problem are encoded by exactly the Moore-Cartan set of G, which is just the thing that I wrote above. So alpha in G of degree 1, such that alpha satisfies the Moore-Cartan equation. So these are the solutions of the deformation problem. And so if you're looking for infinitesimal deformations around a solution, what we should be looking at is, well, this is an algebraic equation on a Lie algebra. So I mean on an actual vector space G1. So it forms so it's a quadratic equation. It gives you an algebraic variety. And what you want is you want to look at the tangent space around a certain point in this Mark-Cartan variety. So you notice that the tangent space at such a Mark-Cartan alpha of the Mark-Cartan space set variety of G just well, it's a quadratic equation. You can differentiate it, and what you get some bracketing with alpha here. You lose the 2 because it's the quadratic part. So you end up getting that this is the kernel of D plus bracket with this element alpha. So I'll denote this by D alpha. And so from our deformation perspective, we're interested in that space, and there is a neat trick to, because you'll see that this is particularly simple if you're actually so 0 is always the solution to the Mark-Cartan equation, seen as living as an element in degree 1. So this becomes a lot simpler when you're looking at 0, because you don't have the bracket with alpha part. So there's kind of a trick to reduce always to such a situation, which is the following. So definition proposition is given such a Lie algebra G and alpha in Mark-Cartan of G. We can twist G by this Mark-Cartan. So the twist of G by alpha is denoted G alpha, which is just the same. So it has the same underlying graded vector space G. It has the same bracket as G, but it has a different differential, and this different differential is just given by the alpha. And what one can check is that this is still differential graded Lie algebra. There's not too much to check, so you need to check that D alpha squares to 0, and this is almost equivalent to the Mark-Cartan equation. Just a nice exercise if you want to do it, and you need to check that this is still a derivation with respect to this bracket but this you don't even use the Moore-Cartan equation. It's the fact that it's a Jacobi identity, actually. So yes, so this insight will prove to be very useful later on, since what we'll be doing is study is to apply this operatic. So what's the plot of this story? The plot of this story is you have operats and cooperats. They're very useful to treat algebras, and they're very useful to construct some Lie algebras that will allow you to address some deformation problems. And those Lie algebras, so G in our situations will be arising from this operatic calculus, will be treated in this fashion. So you will use G and the operatic calculus to obtain the solutions for our deformation problems. This will be more clear in a second. Let me just do first a model category remark. So we're actually doing homotopy theory in all this story, even though not much has been mentioned. But this will, strictly speaking, maybe not play a huge role in what we do, but it's a huge motivation. So there are two theorems that are due to Hinich, which are the following. One is that all that we've seen today essentially forms a model category. So there is a model category on operats, such that one weak equivalences are quasi-isomorphisms, meaning i.e. maps that induce isomorphisms in homology. Is an iso. And sometimes I will just write quasi-isomorphisms by a single tilde, whereas isomorphisms will be denoted by an equal and tilde. And furthermore, that fibrations are surjections. So if you don't know what model categories are, maybe this remark is really not very important, but the point is that we're interested in an equivalence relation that is the one of quasi-isomorphisms, or hopefully morally maybe equivalence relation. This is the wrong word, but we're interested in the relation of being quasi-isomorphic. And this is on operats, but and furthermore, under our hypothesis of nothing inarity 0 and 1, algebras of this form are cofibrant. If nothing inarity 0 and 1,
By Darcy gradient. Oh, okay, you filter by the.
You can always filter by arity.
Oh, you have something in arity one. Okay, good way.
Yeah, but everything is canonically augmented and co-augmented, so there's nothing in arity one somehow. Yes.
These surjections, these are pointwise on the correction.
I'm sorry?
What are these surjections?
Yeah, so surjection, it's the only thing that you can come up with. So for every arity and every degree, it is surjective. And actually, the actual real the actual really interesting property of this story, that's I guess what makes all this it makes everything work somehow at heart, is really the fact that operads of this form are cofibrant, and the proof of cofibrancy is really, you can somehow do it arity-wise to lift quasi-isomorphisms. So it's a really important property. So we like when our operads are of the form cobar of C. Now there is also, classically we're less interested in operads, but more interested in algebras, and the theorem also due to Hinich is that you can fixed P algebras over any operad P also form a model category. And surjections and weak equivalences are, sorry, fibrations and weak equivalences are the same, with weak equivalences equals quasi-isomorphisms, and fibrations are also given by surjections. And furthermore, you have these two theorems are compatible in the sense that if you have two operads that are weak equivalent, so if P to P prime is a quasi-isomorphism, then algebras over P and algebras over Q over P prime are also weak equivalent. Are Quillen equivalent. So it's not even that hard to prove this. Sorry. Sorry.
Don't you need that P and P prime are?
No, not at all. So in positive characteristic, you need some assumptions, but in characteristic 0, this is actually true for every operad, and it's actually very, very nice, because what we like and what we can deal with is with cofibrant operads. So typically, what you actually want to do is you have here some sort of operads, like some sort of algebras like Lie algebras, and you say that, well, Lie algebras, I can find a cofibrant replacement for these L infinity algebras, and you say, well, I'm much happier working in this bigger category, and from a homotopical perspective, I lost absolutely nothing because I know that these are the same. And it's really a proof that you can do by hand. So the adjunction is given by restriction of scalars induction, and the proof that it's an equivalence you can just test on cofibrant objects, and you see that if you do the path there and back, just because bars are compatible with induction and restriction, you can prove this this equivalence without much trouble. I don't actually think this was the proof of Hinich, though. I think he managed to prove this without the operatic calculus. So my time is running out. But right. But the upshot is we like to have cofibrant oprads. There is a proposition that in the adjunction up there, the unit, the co-unit and the unit actually of the adjunction up there. So is a quasi-isomorphism. In other words, given an operad, if you take first bar and then co-bar of it, this is always weak equivalence. So this is a canonical cofibrant replacement. But so maybe you look at this and you say, okay, then we're very happy. We can always have some operad of the form cobar of something, canonically, functorially, and we can, instead of studying algebras over P, I can always just study algebras over cobar of P. The problem is that in practice, this is way too big, and it's very hard to manipulate algebraically, because the whole goal of the operatic calculus is to give you nice formulas to work with. If you end up taking an object, taking the co-free object on it, and then the co-free operad, which is already quite big, and then take a free operad again, you end up with something that is really, really big. The object of causal duality is exactly to find some small c such that cobar of c equals to p. And then, sorry? Yes.
Equals.
No, you're absolutely right. I said equals? Oh, you're even happier then. No, but sure. You want to find a small cofibrant replacement of your operad, and in that case, we say that. So more details should be given, but yeah, my time is over. So so informally, we say that C is causal dual to P, so I should be finishing exactly now, but I will just say one last word, because it will be nice to connect with the following talk from Alexander, which is just give you a theorem or magic. Which is for the nice examples that we mentioned already today, namely Lie algebras, commutative algebras, associative algebras, this problem has been fully solved in, I would say, the most satisfactory way possible, which is Lie is causal dual to the co-operad that is obtained by dualizing the commutative operad, but then maybe up to a shift. And duality is a nice word because it can go in both ways. So similarly, the commutative operad is causal dual to the Lie operad, and the associative operad is causal dual to the dual of it's causal dual to itself. So in other words, just as one final example, this means, I mean, just to spell it out completely, this means that a more manageable homotopical version of Lie algebras will be to consider cobar of this COM dual algebras. Il faut écrire beaucoup plus grand. Yeah, sorry, I clearly am feeling the pressure of the time.
No, pressure.
Yes, so yeah, so concretely then COM dual, we actually consider COM dual shifted down by 1. So this is something that in arity so it's not just you shift everything down, everything lives in degree -1, because then when you co-compose, you need things to respect the degree. So you need to do different shifts according to the arity. So in arity n, this is actually in degree, depending linearly with n. So this is in degree -n, except that then you realize that in arity 1, you have the identity. So you want to stay this in degree 0. So this ends up being in shifted down by degree -n plus 1. And so then you apply this to the Lie operad, and you see that there is an operad that we call L infinity, which is cobar of this dual of COM with this appropriate shift. Into Lie, which is a quasi-isomorphism, and then you look at this, and what is this? So you know what the commutative operad looks like. It's one-dimensional in every single degree, in every single arity. So this is generated by some operations mu2, mu3, mu4, etc. In this is really not nice Blackboard management. And what you do here is you send mu2 to the Lie bracket. And then everything else you send to 0. So what we're saying is an L infinity algebra is something with a multitude of operations that if all of them are 0 but the first one, this is actually just a Lie bracket, but otherwise you'll have some they're satisfying some homotopy conditions such that, well, when you pass to homology, you get exactly a Lie algebra, but it's much more than that. It gives you a more homotopically correct version of this. So if I actually want to write the entire definition of this, you'll find something actually very recognizable as sums of trees. But I think I should stop by now. Thank you.
You know what, maybe we can leave this as an exercise before next lecture. So
Yes.
people have 20 minutes to. Is there any questions in the audience or?
Yes, if there is any question over the internet, it's fine.
Is there any question in the room? Everything is clear? You want to see the core-free C coalgebra? If there is no question, I propose we make a 23 minutes break and we resume at 11:30.
So we're resuming at 11:30 if you didn't hear it online.
11:30.
11:30 in 23 minutes.
Okay. Yeah,